Okay, so we're going to create an isosceles triangle. An isosceles triangle is a triangle with two legs that are congruent. So in this case, I'm using my tool to make segments with fixed length because I want to make sure that I have two segments that are identical. So we have segment AB here. We're going to pick another one that starts also at A and has the same length of 4 units over then that's C. So then what would happen is I could then take a regular segment and connect B and C, and now I have an isosceles triangle. Well, to confirm that, I will use my distance or length. I will measure the distance of each of the sides and see that they're both 4 units. No surprise there. Okay, so what we have here is a special kind of a triangle, isosceles triangle. So let's put that word up there. It's kind of a funny word, and we'll say isosceles triangle, and it is a triangle with 2 legs that are congruent, right? And in an isosceles triangle, okay, these guys right here are going to be the legs. So let's draw them out a little bit with my pen. These guys are going to be my legs, right? So this is a leg. And this one over here is also a leg. Oh boy, it is hard to write with a mouse, right? Now what's this thing called down here? Well, this thing is called the base, okay? The base. Is the base the same length? Well, we can measure it. It doesn't look the same length. It turns out it can be, and when it is, well, then we call this an isosceles triangle, right? I'm sorry, an equilateral triangle. So all equilateral triangles are isosceles, right? But typically you're not talking about. I don't know if I can even get this stuff. Oh, there it is at 4. So that would be equilateral and isosceles, right? But right now I'm just dealing with one that is just purely an isosceles triangle. Okay. So now we have these angles that we're going to look at, and these are the base angles. And what this proof is about is something called the base angles theorem. So let me put that up there real big. Okay. So we're going to try and prove the base angles theorem. Here we go. Base angles theorem. Okay, so what does the base angles theorem? And that's one name for it, is the base angles theorem. But what does it say? Well, what it says is that the base angles of an isosceles triangle are congruent. Okay, so that means they're going to measure the same, okay? So that's what it says. Now, is it true? Well, let's try measuring them, right? We're going to use our measuring tool here. We'll measure these angles. So let's try measuring angle CBA, right? And then we'll try measuring angle ACB. Those are the 2 angles there. It looks like CBA is 46.1, and this other one, ACB, is 46.1 also. Now, what I'm doing, let's see if it's always true. If we move this, we can see that they are going to stay consistent no matter how I move it. Okay? But this is not a logical proof to just kind of, look at examples. What we're doing is we're making examples that kind of demonstrate that, but they're not a logical proof. So how do we prove that no matter how we draw this triangle, no matter what, they're obviously and definitely going to be congruent? Well, what we'd do is we would make ourselves I'll make a triangle right here. Well, we've got a triangle right here. What we're going to do is we're going to make a perpendicular line that goes through, across the vertex and then goes through point A. Now, if that's a perpendicular line, which it should be, let's make sure we just move this. It should always be perpendicular, right? Okay. Now what we're going to do is we're going to find the intersection point. Let's intersect these 2 lines there at point D, and then let's measure A, D, B. Oh, I hit escape here. Let's try that again. Measure this angles. I want to measure angle A, D, B. You can see it's a 90-degree angle there. Okay. Well, what does that mean about angle C? You know, DA, right? What is that other angle? Well, that's got to also be C, D, A, right? It's also, oops, A. It's also 90 degrees, okay? And that's because, by definition, if we said let's draw a perpendicular, we're going to construct it so that it is a 90-degree angle. And that, now, because that's what way we defined it, you know, we're just saying no matter what angle, you know, isosceles triangle we end up with, no matter how it looks or anything else, if I were to move point A, it doesn't matter because we're just saying take any isosceles triangle and construct a perpendicular here. So what do we have? Well, what we have is we have this side, this angle here is congruent to that angle there. But also what we have is we have, you know, we've formed two triangles. We've formed two triangles here. So what do we know about these two triangles? Let's actually look at those triangles, right? I'm gonna make those triangles. So here's triangle ADB, right? And I'm going to actually make a copy of that, okay? Let's make triangle ACD and bring it back here, okay? So now I've got two triangles, right? But what do I know about these two different triangles? Well, let's see. Do I have the rigid polygon tool here? I don't have the rigid polygon tool. All right. Well, let's try just taking a look at them. This triangle here, I know that the leg of this triangle on the left, you know, let's just remember, I'm just going to color in one side. Okay, so this pink triangle here. I know the pink triangle here, that it has a right angle here, and it's a right angle triangle. And I know over here you have a right angle triangle as well. So these two triangles have one thing in common, and that they're both right triangles. So, you know, what I would probably put in my proof, if I were working on a proof here, and I'm going to try to make one here off to the side, is I would say that the triangle, let's see, this was ADB is a right triangle, and angle ADB is a right angle by the definition of perpendicular lines, right? Okay. And then guess what I'm going to do, actually? Probably just do that right here. I'm going to copy all that, and I will go in there and paste it in again. But now I can say the same exact thing about AD, what was that, C? Original triangle was ADC. ADC, that is also, that's the white triangle there, right? And angle ADC and triangle ADC is a right triangle, right? So I know that I have two angles that are congruent. Well, I also know, what do I know? The hypotenuse of those two right triangles are congruent. So I'm going to put that in there. So I'm going to put in, okay, we'll go down here again. Sorry. Okay. And that would be segment, what is that? AB is congruent to segment AC, and that was given. We knew that because it was given to us that this is a set of perpendicular lines. What about side AD? Side AD. Well, this is a good one here. Okay, side AD is congruent to, guess what? Side AD. It's congruent to itself, and this is called the reflexive property. So we know that this side over here is congruent to that side because it was given that this was an isosceles triangle. But we also know that this side of the pink triangle is congruent to this side of the white triangle because it's the same thing. So it's congruent to itself. That's called the reflexive property. Okay, so now we know these two triangles are congruent to each other by something called hypotenuse-leg theorem. Okay, this is a theorem you can use to prove that triangles are congruent to each other. So by hypotenuse-leg theorem, if we know one leg and one hypotenuse of a right triangle are congruent to a leg, the corresponding leg and hypotenuse of another right triangle, then we know that the triangles are congruent. So we know triangle ADB is congruent to triangle ADC. Okay? So now that we know that they are congruent to each other, all of their corresponding parts have to be congruent. So that's the evidence right here. If this is a congruent triangle to that triangle, then we know that the sides that correspond have to measure the same. And we also know the angles that correspond have to measure the same. So we have this angle measuring the same as that angle, and we have this angle measuring the same as that angle, which we knew anyway. But now it proves that this angle is going to measure the same as that angle. So we know by, I'm going to write CPCTC, which means corresponding parts of congruent triangles are congruent. By CPCTC, then angle ABD is congruent to angle ACD. Okay, and that is really our proof right there. That's everything we need. We just show. Let's put that down here. We'll talk through it again one more time real quick. Now what we're saying is, because we've divided this, we've dropped a perpendicular from A down, we've created two right angles here. So now we have two triangles, two right triangles. They're both right triangles. Their hypotenuse is congruent, and they have a leg that's congruent. So we're using this HL theorem. HL means hypotenuse-leg theorem. And if the hypotenuse and leg of a right triangle is congruent to a hypotenuse and leg of another right triangle, then the triangles themselves must be congruent. And then we finally say CPCTC, which is corresponding parts of congruent triangles are congruent. That means the parts themselves are congruent, right? These two parts are going to be congruent. Now, what's interesting about that is sometimes we use CPCFC, and that would be the corresponding parts of congruent figures are congruent. Does not only limit ourselves to triangles. If we have two figures that are congruent, then their corresponding parts are also going to be congruent. Okay, a lot of talking there, but that is your second triangle theorem, and it's a good one, the base angles theorem. It's good to be able to prove it, and then you should remember it because you can use this for many other proofs in the future.